Welcome to the second episode in a series for calculating pi on my relay computer. Here's the journey so far. And it all started with this YouTube comment, which is challenging enough if we're talking about a modern computer, but this is a comment aimed at my relay computer. And my relay computer? It's pretty limited in modern terms. Limited instruction set, basic arithmetic, limited logic, and everything taken 8 bits at a time. But it is Turing complete, or at least the design of it is, and there's a few missing bits I'll need to add during this series, but overall, that's why I'm pretty confident it can calculate pi in theory, but it's certainly not going to break any speed records when and if it does. This is a journey then purely for the love of solving the problem, and that's where this series will focus. Sure, the goal is to see the relay computer calculating pi, but I'm intentionally sharing the journey here of how we get from the idea to the reality. So where did we get to in the first episode? We took a closer look at the value and precision of pi that we're looking to achieve, and we talked through some of the properties and history of pi. We also looked at how infinite series can be used for calculating pi, and as a likely candidate for success, settled on this formula. The Bailey-Borwein-Plouffe formula, or BBP for short. This is particularly appealing as the mathematics involved don't look overly complex, and there's lots of powers of 2, which makes it very binary friendly to calculate. There's one gotcha though, which is the BBP formula produces a result in base 16 like so. That is, it's a hexadecimal fractional value, not a decimal one, unlike the more familiar value of pi above. These values are the same though, or rather, they're very nearly the same, and last time we covered why that is and the challenges in representing fractions in binary. So, what's in this episode? Well, if I'm going to invest loads of time persuading my relay computer to calculate pi, then it makes sense to prove a few things out first. The proof is in the pudding, as they say, and so not only do I need to ensure my understanding of this formula is sound, but I'm also going to want some reference values to verify any result that my computer generates. That will help massively with debugging too, which is something I'll no doubt experience plenty of in time. So I think the one thing I can definitely use as a foundation is the decimal value for pi shown here. This is just lifted directly from the many published results for pi. What I want to check and explore a bit though is converting from decimal to binary and back again. So let's start by hand to really get an understanding of things, and so that we're not here all day, let's take pi down to 3 decimal places. So with rounding, that's 3.142 in decimal, and the task is to convert it into binary, and then from there it'll be relatively trivial to convert to hexadecimal. Just to note that I've tweaked my colour scheme and layout a bit here, but effectively green tables are decimal values, blue tables binary, and red tables hexadecimal. The column headers no doubt give it away, showing the powers of 10, 2 and 16 respectively, and just to help with the decimal, binary and hexadecimal points, I've drawn a vertical dotted line where the fractional values start. Right, so how do we convert? Well, actually, it's not too bad. And let's start with picking off the integer value, as we know that has an exact representation in binary and hex. And with that captured, we can subtract the integer value from the decimal table because we're done with it. So, the way this approach works is we now need to double the decimal value by 2. And then look at the integer column at the left and see if the multiplication created a value of 1. If it did, we enter a 1 in the next binary position, and if not, we enter a 0. Let's repeat that process until we find a 1. There's a 1, and so we take it over. Note also that as we're progressing, the binary digits we've already found don't change. They carry down the table. This is also true for the hexadecimal digits, given they're a direct reflection of the binary values. Note though that we do have to be a bit careful with a hex. The first hex digit represents the first 4 binary digits left of the binary point. Here though, we're only using 2 bits to represent our value of 3, but they all belong firmly left of the binary point. That's also why we've not filled in the hex digit after the hexadecimal point yet. We only have 3 bits of it so far and need a 4th to be sure of its value. Let's move on to the next step then, and as before, we need to truncate the decimal integer. And then times the remaining fractional value by 2, That gives us another binary 0, and we now have enough for our next hexadecimal digit. And 0010 is a hex digit of 2. Let's finish this out now by repeating the same truncate and double approach, which gives us another 0, and then finally another 1. Note that we've ended up with only 2 digits of binary to fill our last hex digit, so we assume the next 2 bits after that will be zeros, giving us 0100 for a hex value of 4. So how's that looking against our previous hexadecimal pi value? Well, that's looking pretty good, with a hex value of 3.24. OK, let's see if we can reverse the process. How does that work? Well, it's not a whole lot different. Let's start with our hex value of 3.24, and we'll need to derive the binary value from that, which we already know is 11.001001. As before, our first step is to pick off the integer part, set that as our first decimal digit, and then drop the remaining fractional part down one row, like so. To get the next decimal digit, we need to multiply by 10, and then pick off any integer value left at the binary point. Righto, multiplication is easy enough in decimal, but how about in binary? Well, actually, there's a trick we can pull to keep things binary friendly. So let's pull our binary down to a separate table ready for our trick. And the trick is to break the multiplication down into powers of 2. And so if we multiply our value by 2, multiply it by 8, and then add those together, you get a multiply by 10 overall. Now that probably looks a bit convoluted, but here's the magic. How do you multiply by 2 in binary? Well, think about how you multiply by 10 in decimal. You shift the decimal point. To multiply by 2 in binary, you can do the same. Or rather, you can shift all the bits one place to the left, which means every bit is now worth double than what it was before, like so. Shift it another place and you've multiplied the original value by 4. Shift it one more place and you've multiplied by 8, like so. This is a handy little trick if we don't fancy doing binary multiplication the long way round, and my relay computer has an 8-bit shift left operation especially for this and similar tricks. We can now add these two results together to get our 10 times result as needed, like so. And then we take that result back up to the top table. And the integer left of the binary point gives us our next decimal digit, so let's pass that over. Great, we're well underway now, so let's repeat the process. We take the fractional binary part again, and shift it left to multiply by 2, and shift it another 2 times to multiply by 8. And finally add together, although there's a problem here, can you see it? We're going to be carrying a bit at the 2's position, so we need a bit of extra room. Right, we can add up now. And first part is pretty easy, and then 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carry 1. Same again, and again, until finally our carried bit lands in the 4's box. Let's carry that up and pass the 4 over to the decimal result. Right, nearly there, let's go for the last digit. Oh, hang on, something's gone wrong. We're expecting an integer value of 2, but that's not happening, and our decimal number is going to be 3.140, not the 3.142 that we originally started with. Wrong, wrong, wrong. What's happened here then? Well, it's that binary fraction problem again. In the conversion from decimal to binary, we've lost precision, and so when we come back the other way, we're short of the number we're expecting. Now if we round our result to 2 decimal places, we do get a correct pi value of 3.14, but we didn't start with 3.14, we started with 3.142. So the important moral of this story is that to get 20 decimals of pi, we'll need to make sure we have enough hex digits to support the conversion. Now, just to prove this isn't all a cover-up, let's up the precision and work it through. So let's start with 3 hex digits this time and see what that does to the binary side of things. Well, each digit represents 4 bits of binary, so 4 hex digits is 16 bits. But I'll ignore the 8's place, as we know the value of pi won't be 8 or higher. Placing the values, the integer 3 goes first, then we place the 2, then the 4, and finally the 3. As before, we're going to convert back to a decimal value, and we'll use the same process as before. But I'm going to speed it up now, as I'm sure you get the idea, but feel free to pause it as we count up the decimal digits, and those turn out to be 3, 1, 4, 1. And there we go. Note that 3.141 is as expected this time because I've started from my original hex value, but either way you can see that extra 3 makes all the difference. So that's how to convert a decimal fraction to a binary and back, but I said earlier that I want to prove out this hex value of pi so that I can verify it before using it as a reference point. So it's the values here that I actually want to convert back and forth, and if you look at the hex pi at the bottom, there's 21 digits in total, which is, ready for this, 84 bits. That'd be fun to calculate by hand. And so this is where I break out the big guns and use a modern computer to check these values and confirm the approach I'm using to convert them. Now I don't see this as cheating, as anything used here will be purely to validate what my relay computer eventually produces. That also means using a binary-minded approach on the modern computer rather than any inbuilt floating point functionality. Anyhow, let's go. And here's one I prepared earlier. As I mentioned in my last video, I work in software engineering and mainly around Microsoft.NET. So hopefully it's no surprise that you find me here in Visual Studio Code with some .NET C# code on the go. It's the thing that's most native to me and quickest for me to get the outcome I need, but you can hopefully see how this would be easily transferable to Python or similar. There's basically 2 key parts to this program. In part A, we convert our known decimal pi value here into a binary equivalent. We then convert that value back to decimal in part B before finally comparing the before and after to confirm the round trip worked as expected. Now, as I just mentioned, I'm taking a binary-minded approach here so that what I learn here has a chance of being transferred to my relay computer. So that means particularly I'm avoiding any .NET floating point types. So how am I holding the binary version of pi then? Well, I've created a custom data type down here at the bottom. And that separates the integer integral part from the fractional part. And that looks a bit like this. The integral part I'm storing in a .NET byte, so 8 bits. The fractional part is a bit more curious, as I'm storing it in a big integer, which is pretty much what it says, an integer that can be as big as you like. That effectively means I'm mapping my negative powers of 2 into an integer with the most significant byte first. Now this is important as it means .NET will keep my value intact and accurate, but also operations like division and shifts, etc. will work as I expect. My thinking here is that between the integral and the fractional part, I'm just simulating a section of memory in my relay computer. As a result, it's really important I also store the precision as part of this type, so I know how many bits of the fractional part I'm using. Same will be true in the relay computer. I need to know where the value starts and ends in memory. Let's take a look at the binary to decimal function. Just as in our hand-worked example earlier, we pick up the integral part of the decimal first. By casting the value to a byte, .NET will drop the fractional part for us. It's not rounding the value, the fractional part is discarded. Next, we initialize our custom type to receive the result as we build it. We then loop around as many times as our precision requires. Just as before, we remove the current integral part, multiply the value by 2, and then capture the new integral part. The next bit might not be so obvious, but we know the integral will be a 1 or a 0, and we want to place that value into the right position in the fractional part of the result. Here we take an integral 1 and then create a new big integer from it. In the example here, we can now shift that left 6 times to get it into the correct position, and then finally we just do a bitwise logical OR with the result so far. By the end of the loop, we'll have filled out the fractional binary bit by bit, left to right. The binary to decimal function follows similarly. And follows what we did by hand earlier, but has a few other tricks to work within .NET. Again, these are things that are going to influence the design of the relay computer program, so the time spent here refining this is time well spent. Let's jump straight to the loop for now, And again, we're going to be iterating as far as our precision dictates. First, we multiply our binary fractional part by 10, and that probably needs another picture again. When we multiplied before, we were creeping into the integral part, but here it's all handled within the big integer type, so in the example here, we go into the 12th, 13th and 14th powers of 2. This all works because currently what we're thinking of as a binary fractional value is just a very big integer to .NET. So multiplying it by 10 is as you'd expect. Now of course, we'll use the times 2 times 8 trick in the relay computer, but the overall effect for times 10 is binary equivalent. To get that integral part out now though, we need to apply some masking, and that's where the two definitions here come in. Visually, that looks like this. And the integral mask just has 1s for the bits that we'd like to preserve, and 0 for everything else. When we do a bitwise AND on the mask and value, it clears everything after the first 3 bits. Now, that's all fine and dandy, but this isn't a value of 4. It's 16,384. How do we get it back to a 4? Well, that's the next line, where we right shift the value into the right position, and here's what that looks like. Here we shift the value 12 times, which in this case would be because the precision is set to 12. We've now got our next integral value, so we need to add it to the result, but here I'm pulling another .NET trick. I'm collecting it as a string, which is why, and it might not be obvious, we set up the string here with the initial integral value and a full stop. Here's a picture of that showing how we would build up a string of the characters 3, full stop, 1, 4 and 1. At the very end of the routine here, we get .NET to pass our string as a decimal value, but this shows an important concept that if we wanted to display the result to a user on the relay computer, it's most likely we'd do it character by character rather than show the result as binary. Final step in this then is to mask out the integral part, leaving just the fractional part of the binary value, and we're ready for another iteration. Okay, quite a lot going on there, and so I've uploaded this code to a GitHub repo so that, if you'd like to, you can take a closer look or maybe even give it a try. Links in the description below. And speaking of which, let's give this a run. And there it is. So let's take a look at the first part first. And here you can see the iterative process of multiplying by 2 and then taking off the integral part. As it progresses, you can see the binary building up bit by bit and the hexadecimal likewise. So what do we get at the end? Well, it actually looks like there's slightly less hex there than I was expecting, but the second part of this routine will confirm for sure. Again, you can see the iterative process of multiplying by 10 and then taking off the integral part with the decimal value building up digit by digit at the right. Again, on the relay computer, it's entirely likely I'll use this approach to display the calculated value of pi to the user, and that's also why I've spent this episode on the decimal binary conversions. No one's going to be impressed if I say, ooh, look, my computer can calculate pi, and then a load of hex plops out. Anyhow, was this particular operation a success? Yes, it was. As predicted, we've actually had to put an extra digit of pi in at the beginning for our original desired value of pi to survive the round trip. But this does now tell me that when I try the BBP formula for pi, I have to get the hex result from part A above to achieve the needed 20 decimal places of pi following conversion. In other words, I've set out the last two milestones, calculate pi in hex to this, so that you can convert it to decimal and get that. So, where's all that got us to? Well, firstly, I now know I can shorten my hexadecimal pi a little bit, because that's the precision required to get me back to the 20 decimal places of pi above. I've also now proven out the conversion between the two, or at least I have on a modern computer, but because I've gone about it in a binary fashion, it's increasing my confidence and understanding of the sort of operations I'll need when it comes to programming my relay computer. Right, that should do it for this video. What's next? Well, the next thing I want to do is start breaking down the BBP formula and have a go at implementing it on a modern computer using binary approaches as much as possible. With that done, and assuming all goes well, I'll then know how to calculate pi in binary, and I'll be ready to start working out how to map all that to the limited functionality of my relay computer. For now though, thanks for watching if you've made it to the end, and I'll see you next time.